Good afternoon, everyone, and welcome to today's joint EOL RAL seminar. I'm Sarah Woods, and on behalf of EOL and RAL, I'm pleased to introduce Dr. Jeff French. Dr. French received a bachelor's in physics and a master's in meteorology from the South Dakota School of Mines and Technology before earning his doctorate in atmospheric science from the University of Wyoming. Dr. French held physical scientist appointments at NOAA in both Idaho Falls and Oak Ridge before returning to Wyoming as a senior research scientist. In his current position, Jeff is an associate professor and the head of the Department of Atmospheric Science at the University of Wyoming. He specializes in observations of cloud and precipitation from research aircraft and the use of those observations to understand cloud processes. He also manages the National Science Foundation University of Wyoming King Air Research Aircraft, a national facility for the study of the lower atmospheric phenomena. Dr. French led several recent field campaigns to investigate the development of cold season precipitation. He was the principal investigator of SNOWY on seeded and natural orographic wintertime clouds, the Idaho experiment, and has more than 50 peer-reviewed publications that include topics on cloud seeding, ice initiation in clouds, aerosol cloud precipitation interaction, atmospheric turbulence, and hurricane development. Most recently, Jeff worked with the EOL through his involvement in the CSER campaign. Please join me in welcoming Dr. French for his seminar titled, "Is it Time for a New Paradigm for Cloud and Precipitation Microphysical Process Studies?" Jeff?
Thank you, Sarah. Okay, thank you for coming to the seminar today. It's actually a 2-for-1 deal today, so we'll be talking a little bit about my work and a little bit about my vision for cloud microphysical studies, process studies. And then we're going to take a little bit of time at the end to introduce the new NSF University of Wyoming King Air aircraft that we have at Wyoming. So the objective of the first talk is really to investigate a new or maybe a different way or look at from a different perspective ways in which we can improve our understanding and or representation of microphysical processes in numerical models. And I like to use this slide to motivate a lot of my talk. So we're going to start with the diagram on the left-hand side. And this came from a BAMS article in 2019, which I believe was like the 50-year anniversary or 100-year anniversary.
It's actually monographs.
Yeah.
For that.
That's right. Okay. So I like the diagram because it sort of describes this unending circle of science understanding and development, where you can start it anywhere on the circle, but I like to start with the observations, and we go out and we make some observations of clouds or whatever properties that we're interested in, and from those we gain some type of scientific understanding or knowledge of what we're observing, and develop some ideas of what may lead to those types of observations or characteristics. And from that we can develop some type of parameterization or numerical representation that we can then put into a numerical model, a model simulation, and run that, which predicts observations that we utilize, or it predicts the evolution of some characteristic then that we utilize observations to test our understanding and representation in numerical models. We often find that our understanding isn't quite right, so that tells us we need to go out and make new observations or observations in different space, and we just continually go through this circle where we're improving with each pass through the circle of both the observations and our understanding and our representation in numerical simulations. And it's more than just aircraft observations, and This diagram was one that I presented at the last AMS Cloud Physics Conference in Madison, Wisconsin, where we were trying to tie aircraft observations and satellite observations and laboratory observations together with numerical modeling studies in terms of understanding how we utilize all of these different tools or strategies to improve our understanding. And an important aspect in this is, particularly with the airborne observations and the satellite observations, is all of those observations describe characteristics. But what we're oftentimes interested in, particularly if we're looking at, I'm not going to use this, if we're looking at modeling and understanding processes, is how the processes that we're trying to get at, which essentially are what define evolution of systems, how those processes lead to characteristics in which we can observe. And really the only thing outside of modeling that really tells us much about processes are laboratory studies. In laboratory studies, we can actually observe a process happening, or we can observe properties at very small time scales to see how they evolve, and from that utilize those observations at these fine time resolutions to make predictions of processes, which are what are needed to input into numerical simulations. Okay? So when we think about a cloud, we have all different types of processes occurring throughout the entire depth of the cloud, and where and when a process occurs is going to really depend on the environmental conditions at that particular location. And as environmental conditions change throughout the cloud, the processes change, and one process may dominate at one time, and another process may dominate 5 or 10 minutes later as the environmental conditions change. And as we make an observation of the cloud, whether it's with a satellite or a radar or an aircraft, we're not observing the processes that are occurring. We're simply observing the characteristics of that cloud at a given time. And those characteristics are the result of all of the processes that have occurred up to that time. We try to use those observations of the characteristics to infer something about the processes, maybe based on the partitioning of mass between liquid and ice, maybe the characteristics of the hydrometeors. That tells us something about the processes that lead up to it, but it doesn't give us the direct information of the processes themselves. So we can really only infer that information, and then we use that to sort of make educated guesses to how we might represent those processes in numerical simulations, feed that through our numerical models, and go back and validate those numerical simulations against our observations. And that then tells us how we may need to tweak our understanding or tweak our representation of these processes. Okay? So what kinds of processes are we looking at? Okay, here's the spaghetti diagram. You've probably seen it before, most recently in a paper by Andrew Gettleman that has 6 different hydrometeor types and water vapor, and describes different processes that are occurring between different hydrometeor types or feed back into the same hydrometeor type. Okay, and you start to look at this and you say, well, maybe we can break down some of these processes. For instance, freezing shows up 3 times in this diagram. So how hard can it be to represent freezing? Until we start to think about, well, what ways do freezing occur? It's not just a singular process of freezing, right? We can have primary ice nucleation or secondary ice nucleation. If we consider primary, we have heterogeneous nucleation or homogeneous nucleation. If we focus on heterogeneous nucleation, then we have contact freezing and immersion freezing and condensation freezing. We have lots of different singular processes, individual processes that are all wrapped up in this idea of freezing. So how do we untangle these processes in numerical simulations? Okay, it requires a detailed understanding of the rates of each of these processes and the environmental controls for each of these processes to determine which one or which ones may be dominating in a particular region in cloud at a particular time. And so most of the way we go about doing this, or a lot of this, has been based on previous laboratory studies, right, where we zero in on one process, we look at very specific conditions, we measure rates, and then we extrapolate well beyond where those laboratory tests were done in terms of the conditions. We feed that into numerical simulations. We look at the results from the numerical simulations, and we say, okay, we're producing too much ice, or we're producing not enough ice. Let's change the rates here, change the rates there. And we essentially have all of these tunable knobs that we're moving. Okay, so even if we can reproduce the characteristics, we're not necessarily reproducing the characteristics for the right reasons, and we don't have a very good full understanding of our environmental constraints of what's going on. So this requires, regardless of how we do this, it requires a combination of laboratory studies, modeling studies, and real cloud observations. So I want to take just a second to review a couple of key findings or conclusions that came out of a recent DOE workshop on the new directions in atmospheric ice process research. And I'm going to read a couple of these bullets here. The first is, a grand challenge in atmospheric research is the understanding of ice processes within clouds, spanning both primary and secondary ice formation and ice growth and evolution. So particularly for folks who've been working with mixed phase clouds, this should be no surprise. This is probably the single biggest challenge when we're dealing with cloud and precipitation evolution, is how we deal with mixed phase clouds. And it turns out that something like 70% or more of the precipitation and cloud systems across the globe are mixed phase regime. Okay, the second is overcoming long-standing barriers in ice process research demands a multifaceted approach to precisely quantify process rates and their environmental controls, okay? And to me, this says, okay, there's ways in which we can do this, but we can't simply do this by looking just at laboratory studies, just at airborne studies, just at numerical models. We have to integrate them, and we have to probably integrate them and maybe even think of new ways to bring these to bring all of these tools together that we haven't utilized before to be able to begin to cover the parameter space that we need to cover. So how do we accomplish this? And I'm going to lean on some of the work that we've conducted or been a part of here over the last 10 or 15 years that deal with cloud seeding as an example of perturbation studies that might allow us to at least explore some of this parameter space that we otherwise haven't been able to. But first off, I'm going to start off with an example where we're focusing on ice process studies, and in particular looking at secondary ice production. So real quick background of secondary ice production. It was recognized 50, 60 years ago that if you look at cloud top temperature and you look at ice number concentration as a function of cloud top temperature, and you compare that with the number of particles, the number of ice nucleating particles that you have in that cloud, that as your temperature increases, as you approach 0 degrees Celsius, you get much higher number of ice particles than you would predict based on your expected number of ice nucleating particles. You have enhancement ratios that are 2 to 3 to 4 orders of magnitude larger than the actual number of ice nucleating particles. So the conclusion from that is, we must be getting ice being produced from some other process other than primary nucleation, right? And this led to the famous results from Hallett-Mossop on Rime splintering. This came from their 1974 paper that showed if you have a grapple particle falling through a field of cloud droplets that have this certain characteristic within this certain temperature range, you can produce a lot of splinters, something like 300 to 400 splinters per milligram of rime that you get on this grapple particle. And everybody was like, oh, this is wonderful, right? This is happening at warm temperatures, so we don't have to be very cold. All of a sudden, we can start generating all of this ice that we had no other way to explain. And the rime splintering as a secondary ice production mechanism, also known as the Hallett-Mossop process, became incorporated in all of these numerical simulations and was utilized as the principal mechanism for describing why we have way more ice in natural clouds than we would expect through primary nucleation alone. Everyone was happy for dozens of years, okay? And there was a few laboratory studies that were done through the 80s and 90s that didn't really seem to be able to robustly reproduce the Hallett-Mossop results. But it was a difficult experiment to do, right? How do you take a grapple particle and drop it through a cloud of supercooled liquid in a laboratory setting and somehow measure the rime splinters? So it was like, okay, it works, it's working fine in numerical models. But it was really in probably the early 2000s and the 2010s that new field campaigns started coming out and new laboratory studies that really began to call into question the validity of the Hallett-Mossop process, certainly as the sole mechanism that was leading to secondary ice production in clouds. This is an example from a recent campaign that NCAR was involved in, Spicule and Escape, I believe, where the Learjet was passing through clouds tops from -6 to -10 to -15 up to about -18 degrees Celsius, where these clouds were developing. Had bases low enough where you're developing drops through collision coalescence, and those large drops were being carried upwards in cloud, and we begin to see ice production at temperatures around -10 to -12 degrees Celsius. And that production of ice was very clearly being, at least in part, due to the fragmentation of frozen drops, which is a mechanism that has been around for a long period of time. Actually, before the rime splintering mechanism, fragmentation of drops was introduced as a possible mechanism, as well as the potential to be able to produce small ice crystals as a shell around a large droplet freezes and ejects ice crystals before complete freezing of that drop. And so this really was probably some of the first observational evidence. Paul had been working on this, I think, with both Andy and Jeff, too, if I remember right, had been working on this for a number of years, dating back to around 2010, 2012. But this paper in BAMS was really kind of the first paper that brought this out to the forefront of, hey, there are other mechanisms that are happening that can't be explained by rime splintering alone. Okay, even more recently was this paper that was published in ACP in 2024 by the German group, where they were trying to reproduce the results of the rime splintering in a laboratory, and they had very, very well controlled conditions where they were taking a drop and elevating that drop and passing supercold, or not drop, but ice sphere, and elevating that, or suspending that, and passing supercold droplets across that, and trying to measure the number of splinters produced. And they did this over a range of temperatures between about -2 degrees Celsius all the way down to -15 degrees Celsius. They did this with a range of cloud droplet sizes and a range of ice spheres. And what they found was, under none of those conditions were they ever able to reliably reproduce ice splinter production in this cloud. Okay? I think the most they got was something on the order of tens of ice crystals, or less than 10 ice crystals produced, compared to Hallett Mossop's results of 300 to 400 ice crystals being produced per milligram of ice. So it was this paper, in my mind, that really first called into question whether the Hallett-Mossop process, whether the Rime splintering process is even occurring in clouds, whether that process is even a valid process, okay? So now we're looking at some data that was collected by the Canadian NRC Convair 580 during the wintry mix campaign. And here we're looking at two profiles through the cloud. On the left-hand side, we were ascending through a stratus cloud from a base of a cloud that was around -5 degrees Celsius up to a top of a cloud that was about -15 degrees Celsius. And on the right-hand side, on the blue side, we're descending through that cloud, okay? And what we have here is the temperature profile is on the left, and these are images from the 2DS. So across one of these buffers is 1.3 millimeters. So at the top of the cloud, we have relatively small drizzle, or very large cloud droplets that are on the order of 80 to 100 microns in diameter. And as we descend through this cloud from -15 at cloud top and get into warmer temperatures, we see that these drizzle particles are growing, presumably through collision coalescence, as they fall through a field of cloud droplets, until they reach a maximum size on the order of about 400 to 500 microns. 400 to 500 microns in diameter, around a temperature of -8 degrees Celsius. And then somewhere between -8 degrees Celsius here during our descent and -6 degrees Celsius, we get this very rapid transition of these large drizzle drops, 400 to 500 micron size drizzle drops, to these columnar type crystals. Now we're only plotting on here the particles that are larger than 300 microns. Okay, so there's a number of small ice crystals that are also columnar type on here that we're not showing in this diagram. But by the time we get down to a temperature of -5 degrees Celsius, our cloud has completely glaciated. Okay, so we get a rapid transition between between -7 degrees and -5 degrees of large drizzle and cloud water to a completely glaciated cloud, all of columnar type crystals. Okay? Looking through the same cloud, now we're zooming in on the area between -7 degrees Celsius down to, it got cut off here, but this is about -5 degrees Celsius. And we're looking at particle size distributions in orange of liquid particles, in blue of ice particles. So we've used circularity and sphericity from OAP probes to separate liquid from ice particles and plot out the distributions. And what we see is near the -7, -7.5 degree region. Most of our mass is in the form of liquid particles, and if we look far over here on the left-hand side of the screen, this is our bulk mass. We'll see that roughly 3 to 4 times of our bulk mass in liquid compared to the amount of mass that we have in ice particles. As we descend through the cloud, the liquid mass decreases. Eventually, the ice mass starts to pick up, and when we get down to about 3.5 kilometers, or around -5 degrees Celsius, our cloud is dominated mass-wise by ice. And we also see that in the evolution of the distributions here on the right-hand side, where the mode of liquid drops sort of that sits between 200 and 300 microns remains, but decreases in concentration by an order of magnitude. And we start to pick up both small ice that is about 100 to 150 microns in diameters, and we have distributions that extend out to 1 millimeter in size as those ice particles grow very quickly in a field of liquid droplets. So they're able to grow both through accretion as well as through depositional growth. Okay, one more piece of evidence from this example. Here we're looking at an FFT spectrum from a vertically pointing radar. So we're looking at the velocity as we look up. And we see from the cloud top at around 5.5 kilometers, the vertical velocity, the fall velocity of our particles increases rapidly to about 3.8 kilometers. Okay, that's tracking the growth of those drizzle drops that are growing through collision coalescence. And then all of a sudden at about 3.8 kilometers, we get this rapid widening of our velocity spectra and a shift to smaller velocities, right? Which is very indicative of a glaciation event that is occurring as our fall velocities decrease. And it widens at first because we have a mix of liquid and ice. And then by the time we exit the bottom of this region, we have a very narrow distribution centered at 1 meter per second, which is consistent of what we would expect from an ice, a glaciated cloud. Okay, so that's an example of, hey, we've seen a number of experiments that suggest that rime splintering might not be occurring, but we have another example that fits perfectly within the idea of rime splintering, okay? There's no other mechanisms that can readily explain what we see in terms of the rapid glaciation, especially associated with that temperature regime that we're looking at. So the question becomes, how can we combine laboratory measurements, cloud chamber studies, observational cloud and precipitation measurements in the real atmosphere to improve our understanding of processes? Or observation and modeling how the clouds and precipitation respond to perturbations in otherwise natural conditions may be a route to be able to begin to investigate factors that influence or control these processes. And this is where I want to introduce a little bit of the observations that we took in Snowy. So Snowy, the seeded and natural orographic winter times cloud study. The Idaho experiment was a cloud seeding study where we're introducing silver iodide into an otherwise natural orographic cloud that is occurring over the mountains, and we're introducing that through the use of a seeding aircraft that is flying perpendicular to the wind, this red line here, releasing seeding material on the upwind side that then gets carried downwind through the clouds in a temperature regime where you would expect the silver iodide to be active as ice nuclei, and in a cloud that has otherwise relatively low natural ice concentrations. And the prediction coming out of that is because we're releasing this as the aircraft moves back and forth and this seeding material advects downstream, we should see this zigzag pattern. Or if we fly back and forth with the King Air through this zigzag pattern, we should see very well-defined regions that have been impacted by silver iodide, and indeed that's exactly what we did see. So here we're looking at the vertical cross sections with the Wyoming cloud radar at a time span of about an hour and a half downwind of the mountains. And I want to point out two signatures. This signature that showed up at 1651 that advects a little bit further downstream at 1658, and about 20 minutes later at 1718 with a second one showing up. And we're able to track these downstream and look at the evolution of the reflectivity pattern with time as these seeding signatures move downstream. And because we're flying back and forth through it with the aircraft, we're also able to make in situ measurements, and we're able to see that when we fly underneath these regions during our first penetrations, these regions are dominated entirely by liquid water contents on the order of 1/10 to 0.15 grams per cubic meter, but they rapidly glaciate as that seeding material spreads in depth and converts all of our liquid to ice, and we get relatively high ice water content observations up to about 0.4 to 0.5 grams per cubic meter as this evolves. And we did this for a number of cases. So here's another case where we are making penetrations at the top of a cloud, and this is an interesting case because the other case was entirely the static response to the cloud. Here we make a penetration right at the very top of a cloud, so we're skimming, or we're actually above the top of a natural cloud, and we pass through a region where the top of the cloud sticks up about 300 to 400 meters above the natural cloud, and we can see this based on the ground-based radar image at roughly the same time. And so we're passing through an area that has been influenced by seeding, and due to the fact that conversion of mass from liquid to ice releases latent heat, and we're in a region with some potential instability. That gets realized by generating an updraft, convergence in the center here, toroidal circulations around the outside, and this increase in the cloud top height of about 300 to 400 meters. And as we pass through that, we can see that our cloud at the very edges is dominated by liquid or mixed phase regions of ice crystal concentrations that are on the order of 400 to 500 per liter. So this is 2 orders of magnitude larger than the natural ice concentrations that we were measuring in this cloud on that day. And then in the center of the cloud, we have significantly lower ice concentrations, but we have larger particles that have grown entirely through, or mostly through depositional growth. So we have pristine crystals in the center of the cloud that are falling out of the cloud. Then towards the edges of the cloud, we have smaller crystals with much higher concentrations that look to be a mix of pristine crystals and lightly rimed crystals, as much as we can tell from the OAP images that we have. So another experiment that I want to point out in terms of how can we utilize perturbation studies possibly to get at an understanding of ice processes. So this is a study that was reported initially in BAMS by Jan Henenberger and his group at ETH Zurich. The experiment was called Cloud Lab, and it took place on the Swiss plateau, where you have a very stable supercooled stratus cloud that occurs in a temperature regime of about -5 to -20 degrees Celsius. And they move on the upwind side. They utilize a small drone to release silver iodide and allow those silver iodide particles to drift downwind over their ground-based site, where they have a tethered balloon that can make measurements in cloud, and also have a ground-based radar where they can measure characteristics of the cloud. And based on the length of time that it takes for the silver iodide, the seeded region, to evect, they can back out process rates, growth rates of ice crystals, nucleation rates, etc. So here's an example from that experiment. An example from that experiment where they're looking at radar reflectivity from two different seeding experiments, one where they seed 6.5 minutes upwind, and another where they seed 9.5 minutes upwind, and they can look at the development of the reflectivity. They can also look at the liquid water content and the ice water content, so liquid in blue down here, before seeding and after seeding. This is the ice content, in blue, and the liquid water content in red. So you see that the liquid actually doesn't change, but the ice increases significantly. And they can also look at the development of the distributions. And from those developments of the distributions, they can back out process and growth rates by comparing how the distributions differ from a 6-minute experiment to a 9-minute experiment. Okay, so that gives an idea of how process studies can be utilized, but how can we control them in a way that we can actually begin to test different types of processes or perturbations. And at Wyoming, we're working on developing an idea where we combine a ground-based mountaintop lab with our airborne measurements and with our ability to utilize the NCAR Wyoming supercomputer to do numerical simulations, and doing perturbation studies upwind of this lab. So this is a picture of the Elk Mountain Observatory, which sits atop an isolated mountain in southeast Wyoming, west-northwest of the Snowy Range. Turns out this observatory was built in the late 1960s, particularly for this type of work, as cloud seeding work funded most of the cloud physics work back at that time, but has largely remained unused since the mid-1990s, at least for cloud studies. So what we would like to do is we would like to begin reproducing some of those early studies from the 1960s for cloud perturbation studies, but now utilizing it with the new technology and the new instrumentation that we have available to us nowadays. So we can instrument at the top of this mountain, and we can release aerosols at the base on the upwind side of the mountain. We can utilize tracers within those aerosol releases to track when they pass over the observatory and measure changes in the cloud characteristics. At the same time, we can fly through the cloud and above the cloud with our aircraft, utilizing both remote sensing and in situ instrumentation to be able to look at the dispersion of these particles, as well as looking at the spatial evolution with time of these particles. And then all of that then would feed into numerical simulations utilizing the NCAR Wyoming supercomputer to be able to utilize different process rates to look at our prediction and our understanding of clouds. And this can be started pretty easily with something like silver iodide, but one could imagine doing other types of aerosol perturbation studies with this setup as a natural laboratory to investigate cloud response to aerosol perturbation. And that's the end of this talk. So I'm going to spend about 10 or 15 minutes just introducing the new NSF University of Wyoming King Air research aircraft. And very brief history. So for those of you who don't know, the University of Wyoming has been operating atmospheric research aircraft since 1965. We started with a C-45, which was replaced in the 1970s by a Queen Air in early 1970s, and then replaced in 1977 by a B-200T King Air aircraft, which we operated for 45 years until that aircraft was retired in summer of 2022. That aircraft, the King Air 200 N2UW, became part of the NSF fleet in 1987, and from 1987 through 2022, we operated it under many different cooperative agreements over that time with the National Science Foundation. It's a versatile aircraft. Its primary mission, at least when it was originally developed, was to study cloud physics and dynamics, but has it expanded over time to include boundary layer turbulence, air quality, trace gas chemistry, remote sensing, and education and training, being the only national facility aircraft that's based at a university now. That aircraft is utilized a lot for educating and training new scientists, especially those at the University of Wyoming. So a number of folks that work in the field of airborne atmospheric research get their training at the University of Wyoming as graduate students. This is the future of a Wyoming King Air. This aircraft will be coming online this year. Right now, its first scheduled project is next summer. It had been scheduled for this summer, and we recently just had to kick back that project, which was a very painful decision for us to make. But I want to talk just briefly about its capabilities and where we're going with this aircraft. So the aircraft is built on a B-300 base aircraft, which is a King Air 350i. The aircraft was used 2013. It had about 1,200 flight hours on it, so it was a lightly used aircraft. Shortly after purchase of the aircraft, we upgraded the engines to larger PT6-67 engines. We increased the max takeoff weight from its standard 15,000 pounds to 16,500. We upgraded the avionics. We added additional fuel tanks, etc. We have some of the anticipated performance characteristics down here on the lower left. This is a timeline of the development of that aircraft. So we actually began the discussion of a replacement aircraft in 2013, and we did a lot of early work on identifying the aircraft platform and identifying what type of modifications we were going to make to the aircraft, and went as far as visiting potential vendors for modifying and certifying the aircraft in 2017 and 2018, before we even wrote our first proposal for the aircraft development. We proposed this to the National Science Foundation in 2018 and were awarded an MSRI in 2019. We purchased the aircraft in 2020 and then selected the vendor for making the modifications and the certification, and had them begin to install sort of off-the-shelf STCs, everything that's listed here on the left-hand side, which were certifications and upgrades that were available already. For the next 3 years, 2021 through 2023, we worked with the vendor to complete the design and installation. This should read 60 plus research-specific modifications. Those modifications were completed in mid-2024 when we moved the aircraft into flight testing. And the aircraft was delivered to the University of Wyoming in late 2024. And the latest news is just last week, we were issued our supplemental type certificate for the installation of, or for all of these modifications and the provisions associated with them, which will allow us now to begin certifying instruments on the aircraft and testing, which we expect to continue through this year. So each of the research modifications are indexed with a number, and you can see on the left-hand side all of the external modifications. You can imagine a number of holes on the fuselage, top, bottom, side, etc. We have wing pylons on the tips of both wings that are capable of carrying probes at 3 locations on each of those pylons. We have an extended nose that has a number of instrument pads around the nose that will allow us to install instruments on the nose, and we have a nose boom that will house a gust probe for measuring winds and turbulence, as well as a number of modifications inside the aircraft, such as overhead rails, an upgraded mission electrical system, etc. So 60 plus of those modifications. And for all of the external stores, we wanted an ability to mount instruments on the external locations without having to test fly every new instrument. So we came up with shapes that had some maximum area, frontal area, side area associated with them, maximum size associated with them, weight, etc. And then test flew those shapes through 550 or so different test conditions. And from that, we were able to, or our vendor and test flight pilots were able to come up with performance charts and performance degradations based on what you were flying at any given location and the performance or the drag associated with the instrument at that location. So here's an example from our flight manual supplement that helps define our limitations. So this chart on the left-hand side shows 40-some odd different locations on the outside of the aircraft, and I highlight just one of them. This is at the base of the nose sensor. And what this tells us is that we can put an instrument there that has a maximum frontal area of 59 square inches, a maximum side area of 24.5 inches, dimensions that don't exceed this length, width, and height, maximum weight, a maximum drag. So if we have an instrument that fits within that envelope, we can fly it at that location and we don't need to test fly it. We just need to certify the instrument itself. But no additional test flying is needed for that. Same thing with the wing pylons. Here we're out on the right-hand side of the wing. And you can see that we can have a number of different loading on the wing. So we can have instruments at all 3 locations on the left wing or the right wing, or 2 locations on each, or 1 location on each, or 2 on one and 3 on the other, etc. That defines our limitations. And an example of performance adjustment basically says, okay, so when we put instruments on the outside of the airplane, we have to decrease the maximum takeoff weight of the aircraft by 500 pounds. And then for each drag index count, we have to decrease our takeoff weight by 5 additional pounds. So if we're running with 100 drag counts, we have to decrease our max takeoff weight by 500 plus 500. And that accounts for the performance degradation. We also have performance degradation charts that deal with maximum runway length. They deal climb rates, etc. The second document that came out as part of this STC is called our Sensor Stores Provisions Installation Limitations Manual, the SPIL for short. And this defines for each location what our limitations are for that given location and the process by which we must go through to certify a payload at that location. So this is an example of our wing pylons. We have 3 different locations. We have an inboard location, an outboard location, and a center pylon location. And if we look, for instance, at the center store for inertial loading, we are allowed a maximum weight of 70 pounds. The CG has to lie within these fore-aft limits related to the location flight station, the up-down limits related to our water line, etc. And then we also have area limitations, a maximum frontal area, a maximum side area, with a centroid that must lie within these locations. So if we, for instance, take an instrument such as our KPR radar, and we want to mount that in the center location, we can see, okay, this is the weight, these are the this is the CG in the aircraft coordinate system, this is the maximum frontal area and the maximum side area. And we come across these charts and we say, okay, this is what our limits are, and this is what we have for the KPR, and it fits within all of those limitations. So our structural engineer is going to capture all of this in a report and show that if we bolt it on with these types of screws and fasteners, it's not going to fall off. We have an electrical engineer that will go through and look at the capacity of our circuits out there and show that we're within our certification guidelines for that. We have an icing engineer that's going to look at the drag that gets built up due to ice buildup on the front of this. And we have a performance engineer that's also going to do an 8110 that defines what the drag characteristics are. And as long as all of that gets done, then that package goes to our maintenance team, and our IA is able to install that instrument on a field approval with a 337, and no additional FAA certification is required for that. Okay, so this spill manual, and this is the last slide I have, covers the installation of any external store, and it simply requires what I just said, an analysis and a company 8110-3 for structures, performance, electrical, and for flights into known icing condition, icing certification. And when the analysis demonstrates that the store is within the limits, it can be installed via 337 on a field approval. And on the right-hand side is the copy of our STC for this aircraft, which was issued just last week. And I think that is it for the slides, and I'm happy to take any questions.
Your video screen. You don't have to pass the mic here, so are there any in-room questions?
Yeah, 2 things I want to mention.
Yeah.
One is I'm a big fan of Lagrangian spiral descents, where the aircraft basically follows the wind, descending at about a meter and a half per second. And you can look at things like ice aggregation, fragmentation, and change from mixed phase to all ice conditions. So that's a very useful flight pattern.
I agree 100%. And unfortunately, the data that I showed from the wintry mix experiment was not done on that type of flight pattern. It was a straight flight pattern because we were actually en route to our region of study at the time. So these data that we collected were sort of not necessarily what we were looking for, but they were sort of this opportunity that we had en route. But I agree with you 100%. And that's one of the things that we're struggling with in terms of interpreting that data, is how much horizontal inhomogeneity might have there been in that cloud. We're trying to characterize that based on the radar observations.
Just one other point, and that is we participated in the impacts field program studying East Coast snowstorms, and we have a paper for early submission JMC, where what we did was we flew just above the melting layer and just below in updrafts. And what we found was that the aggregates more or less have a very slow path through the melting layer. And so what we found was they release fragments, ice fragments, which then can be carried up in the updrafts and be copious secondary ice producers.
Yeah, and I think in a lot of cases that might be happening. And I think in the case that we looked at, that was not happening because we have this cloud that's entirely liquid above, and we get this transition to ice at a temperature that's significantly colder than 0 degrees Celsius, but significantly warmer than we see through the depth of this otherwise super cool liquid cloud.
But it looked like the Doppler data could suggest there were updrafts in there.
There definitely were updrafts in there, but we still would have needed that initial formation of ice process to occur somehow, right? So I mean, a good point, and maybe the point that you were trying to make is there very well could have been multiple processes, right, that are occurring here that lead to the observation that we made, and we shouldn't always be thinking about a singular process that leads to this. So.
I thought the vertical analysis of the fall velocities was a really interesting and cool way to see the transition from like falling drizzle to maybe a broader distribution of ice particles that have slower sedimentation rate. So when making that plot, were you always using like the closest gate to your aircraft as you descend or ascend, or how was that plot?
So that particular plot was based on a ground-based radar. Okay, so the ground-based radar was set up to do volume scans, and then per one volume scan, it would do a vertical look. So every 6 minutes, we have a vertical look where we would be able to collect the full Doppler spectrum. So basically every 6 minutes we have a vertical look. And the interesting thing about that is this was a very transient effect. So we would see it at one time, and then the next 2 vertical looks we wouldn't see it, and then we would see it again. So that what that was suggesting, at least to us, is that this effect of this rapid glaciation, if we're interpreting that correctly, that signal was transient. It would occur for a few minutes, and then it would go away, and it wouldn't occur, and then it would occur for a few minutes again.
I want to comment on one of Andy's comment about descending down through the cloud, because that was a favorite flight path of John Marowitz.
Yeah.
But it originated from a guy named Passarelli. And the idea is that for a lot of fall speeds, you can actually match the fall speed with the aircraft. So you're descending at the same rate as the particles, and able to watch their evolution as they go down. And so I mean, the key to it is not just going down, but actually to be able to use the airplane to track a particle downward. which you could adjust in real time, although a lot
Yeah.
of the unrined particles have similar fall speeds.
Right. Yeah.
But that was a huge thing that John would like to talk about, so
Yeah.
you go back to the history of the plane, things that were done with it.
Lots of history there. Well, that's the end of our hour, so respect for people's time. Let's thank Jeff one more time. Feel free to have more side conversations over the cookies.